and I work with the University of York, the Cambridge Hospitals, and the Florida Atlantic University, the Center for Complex Neuroscience Research. My approach to 3D is slightly different from what I've seen so far. My approach to 3D is more to do with the motion rather than static depth itself. So I work on human gait, and from literature we know that human gait carries information about identity. It's sort of like a gait fingerprint. It's got gender, the state of health. For example, if you have any diseases like Parkinson's, osteoarthritis, the style of your walking changes, and also the intention and emotional well-being. If you're feeling upbeat or if you're sad, the style of walking definitely changes. And I'm sure everybody's comfortable with the motion capture technologies. There's wearable sensors like accelerometer gyroscopes. There's marker-based Vicon, OptiTrack. I happen to work with Vicon. And there's also markerless tracking like the Kinect or the Orbec, or now that the Kinect is out of commission, more like the Kinect version 4. So I work primarily with Vicon and Kinect in order to study walking styles. The inertial sensors, they have low power consumption, they're portable, the patients can wear it on their bodies and go out there in the field. But the problem we found so far is of low patient compliance. The patients just don't bother wearing the watches and the bracelets, and they just forget. And they go around, and then we have a lack of data, and we have a big hole that we don't really know how to fill it up. So the standard approach, we thought, was with all the collaborations in hospitals that we have, we're just going to have patients come into the lab, walk in front of Vicon cameras, Kinect cameras, and then collect data on the fly. So that ensures high patient compliance because they have been slotted, they have been given events and times, and if they miss out, then the NHS system basically taxes them, saying that you did not show up into when you're supposed to show up to the hospital. The problem with markerless technologies, especially Kinect sensor, is when you perform the joint detection, for example there, especially on the feet, the accuracy is not as great. But in my case, because I'm working on walking data, I get lots of data about the same event, because gait is a very periodic activity. And if you pass it through 12 Hertz 3-order Butterworth filter, the accuracy when compared to Vicon is not as bad. It's clinically viable. Currently, the Cambridge University hospitals, there's a gait lab, and the clinician we work with, he puts the markers on the body like a standard Vicon type system, and simultaneously also takes data from a Kinect sensor. And he has, or as the NHS system has, they've got clinical metrics which they derive from walking, and they compare it with what normal walking should be. And then they tell you if your walking is good, bad. But this is all on paper. It's mostly qualitative, and it's mostly to do with the doctor. So if the doctor is new and doesn't have much experience, they're going to rely on the clinical gait metrics. And unfortunately, it does not capture the tiny subtleties of change that the doctor would visually see, but the gait metrics would miss. So then we figured we can always use machine learning approaches. We've got standard support vector machines, decision trees, which could then be trained on gait metrics, clinical gait metrics, prescribed by the NHS. Or we've got deep learning models. We've got the feed-forward standard multi-level perceptual models. And the second one, which was more interesting for us, is the recurrent or the LSTM networks. And we know that this, if we base our machine learning network around LSTM, and we took LSTM because time and again it's been proven to perform much better than RNNs. We realized that if we put it around the LSTMs, it should, on paper, have the same perception capacity that humans do. So basically, it should be on par with human clinicians. But we were not sure about this, so we decided to conduct a study. It was a dummy study where we got people, it was mostly healthy people from university students and staff. And we got a bunch of them, and then we recorded their walking styles. And we wanted the networks to figure out if the walker is a man or a woman. The reason we came up with this gender discrimination is firstly because it's been extensively studied in the past. So if we go wrong, so we know for a fact that they can be discriminated. And secondly, there's no study which compares direct humans versus machines in terms of gait analysis yet. So we knew that we had something new there. And second, and thirdly, it's a good testing ground for various machine learning algorithms, which was our objective to begin with. So we divided all the models into two different segments. The motion perception-based ones, which basically can see motion in time and then take a decision, like humans, or the LSTM networks. And we've got the standard models, like the SVMs, decision trees, and the feed-forward neural networks. But based on the style of inputs, we divided them into static and dynamic, which is the title of my presentation today. So the data set was pretty straightforward. 41 people, they were asked to walk for 12 minutes on a treadmill. First 6 minutes, I set it up at 2.3, which is considerably slower than normal walking speed, because anytime anybody has a disease, they end up walking slower than they normally would. And for the next 6 minutes, they were allowed to choose the treadmill speed themselves, whatever they were comfortable with. And the motion was captured using a Kinect sensor, a normal standard Kinect sensor, and we used the Microsoft API in order to extract the joints and recorded those as temporal evolutions of the 3D Cartesian coordinates of the joints. For the static models, we got the Gait Metrics that is used in the hospitals currently to see how much information do they really have. And then we had the standardization, normalization, all the usual processes that you do before you feed it into any sort of machine learning network. For the dynamic models, for humans, we converted it into point light animations because it's been proven in literature by Frank Pollock or Johansson, who did the studies on point light animation, and they proved that humans are good at picking up gender from just point light animations, basically joints showing up as white balls and everything else is black. But the one thing that they commented on is that humans rely on optical flow when they're trying to understand motion. And we did not want to disadvantage the LSTM networks. So we gave it first order and second order differentials of the point data to see how it performs, or what is readily available to the LSTM networks to extract right from the positions or the velocity or the accelerations. We did the standard processing again, 12 Hz order 3 Butterworth filter in order to get rid of all the high frequency noise. All the values were standardized and normalized. Humans, they were shown something similar to this. There were 22 observers, 250 clips per duration, and I'll come back to this point, duration, later on. But basically, this would go on for a while and then would stop, and then they would have two buttons on screen to guess whether it's a man or woman. It was a simple experiment. LSTMs, feed-forward neural networks, just a high-level description of the optimizers, the learning, and what the architectures were. Support vector machines, we tested it on 3 different kernels, and decision trees was ID3 decision trees, and then later on we went into C4.5 and J48 in Weka. The training and testing is every time we took 2 men and 2 women out of the set as testing set, and we trained on the rest, and then saw how it performed on the testing set. And we did this multiple times. And the models I developed was in TensorFlow, PyTorch, on the standard machine learning libraries. And this was the result. Turns out that the LSTMs, when trained with not the position data, but the velocity data, are better at extracting gender from the style of walking. And humans, in fact, all the LSTM models were just much better than humans at extracting gender from walking styles. And humans are way down here The PAT signature is something that we came up with later, which I'll explain in a second. So we knew that, okay, so we know what sort of network to build. We need to build an LSTM network. We were super excited about the results, went to the doctor, and we said, hey, look, we can identify this, so let's start let's start clinical trials and start collecting clinical data. And the doctor asked, that's great, but why does it have about 90% accuracy? What is it picking up that I'm not able to pick up, or humans are not able to pick up? And we didn't have an answer. So we're like, we don't know. It's just learning something that humans are not. That does not fly in a clinical context. They said, well, if we deploy this in a hospital and we misdiagnose a patient, who gets to blame? Does the hospital get to blame? Can we blame you? Or will I get blamed? So what's going on here? So we realized that even though the deep learning approach was amazing, it did not really solve the practical problem. So we went back to the whiteboard. And, all right, but before we come to that, we also said, well, the LSTMs are not just great at identifying gender, they need much less data than human when coming to a certain gender performance. So this is human perception of gender, and the more data we feed in, the better it gets. LSTM just gets really good. So we went back to the whiteboard, and there were three options that I figured. We could convert them into spectrograms, or extract wavelets, or I could get path signatures. And path signatures is a concept that was inspired by Terry Loyne's rough path theory, where it's sort of a path integral, but not really. The advantage of it is it's highly time scale invariant, so I can apply it to any algorithm, be it Vicon, Kinect, or any of the inertial in any IMU dataset. And this has already it's been studied in human action recognition, and it's been very successful so far. And this was done in human action recognition, financial time recognition, music compression. So I know that this works. And the advantage of this is it's very interpretable. Like, you know that it works, and you also know why it works. So this was the second static feature extraction technique that we used. And we used the J48 or C4.5 as it's more commonly known, decision tree in Weka when coming to this interpretation. And we did the same study. We gave it walking data, extracted the path signatures, and then asked it to guess whether it's a man or a woman. And the accuracy was not as good as the LSTMs, but the advantage is we got to see why it thought somebody walking was a man or a woman. And it turns out that it's basically the shoulders. Like, men sway their shoulders way more than women. And when men walk, they happen to always walk, they bob up and down a lot, which gives a very high value to the path signature when it comes to the hip base. And we could also correlate this with literature, with medical journals and neuroscience journals have actually studied the same thing. And it turns out, at least the misconception that I had, was before I started any of this study, I thought men sway their shoulders more, women sway their hips more. It turns out hips sway is not as important as the shoulder sway. So we figured that, okay, LSTM, deep networks, they work amazing, they do everything, and if there was a situation where we just needed to classify, and we didn't really care to look inside the mind of the network, then we would just go for an LSTM. But if we do need to look into why it's classifying, then we're better off sticking to a static approach and using something like path signatures. And LSTMs have a much higher learning efficiency as compared to humans. Considering humans are evolutionarily supposed to, it's debatable, but they're supposed to identify gender from afar. So basically they're supposed to be really good at figuring out if you're a man or woman based on the style of walking. What's next? So the doctor was super happy, and we're collecting data. about two kinds of patients now. One is stickler patients. They're basically patients who have a genetic condition which predisposes them to develop osteoarthritis later in life. We're doing this at the Cambridge University Hospital, and at the York Hospital, we're collecting data from people who have been diagnosed with osteoarthritis. So we know that there's no ambiguity about how to label them. And as a future study, we will be comparing them with the decision of the clinicians, having shown them the same data. We're also testing on Vicon and OptiTrack. I haven't got that yet, but we have access to the Vicon system in the Cambridge University Hospital, so I will be testing on that sometime very soon. And this, I realize, is the expertise of this room, extracting 3D data from monocular cameras. That's also something that we would be exploring in the future. Thank you.